Hi everyone, welcome to another educative lecture on this channel. Today we'll be treating the topic how to calculate and draw bending moments and shear force diagrams using three-moment equation. This is part 1. In this lecture you will discover how to carry out three-moment operations, the principle behind three-moment equations, like what we have here. Once we have something like this is a continuous span. The principle, you take it span by span and then you analyze, then still using the equations that was this is the expression for two spans for a continuous span. This is the expression you are going to use. So you are going to understand how to use this expression, the principle behind it, and also using it to draw the bend moment and shear force diagrams. As you see here, the bend moment and shear force diagram. If this is what you are interested in, kindly like, share and comment on this channel. If this is the first time of joining this channel, I say welcome, and if you are a returning subscriber, I say thank you very much. Kindly share this content to others so that they can benefit from it. Okay, so we are going to dive into the main thing we are here for. That is the three-moment equation. Let us understand what three-moment equation is, how the principle behind it, and then how we can actually apply it. So now, from what I have here, I said the three-moment equation is a fundamental tool in structural analysis, particularly useful for analyzing continuous beams. It was developed by the French engineer Émile Clapeyron in 1857. Now, it allows engineers to determine the bending moments at the supports of continuous beams, considering various loading conditions. This equation helps in achieving statically determinate solutions for indeterminate structures, making it crucial for ensuring that the safety and the efficiency of structural designs. Okay, let me explain this. The three-moment equation was developed by French engineer Émile Clapeyron and is useful for continuous beams. Now, I remember explaining what statically determinate and statically indeterminate structures, what they actually stand for, what they mean, and how we can analyze it. For statically determinate structures, we can only use equilibrium methods to solve it. While indeterminate structures, we have different methods. We have the moment distribution methods, we have the three-moment equation, and other methods. So this one we are using the three-moment equation that was developed by the French engineer Émile Clapeyron. So the three-moment equation relates the bending moments at three consecutive supports. This is the condition. It's taking three supports, that is two span, three supports of a continuous beam subjected to external load, something like this. This is 1, 2, 3, 4. This is 4 supports, 3 span. So when you are using three moment equation, you take the first three, 1, 2, 3, that is ABC, span L1 and L2. You now express it using the expression developed by Clapeyron. Then when you are now doing the second part, to include D, you take from B, C, and D. If you have other support, you continue like that. This, and the next one. So I hope you understand that statement. So after breaking this down, then the principle of equilibrium can now be applied, since that will be broken down into statically determinate structures. So let's look at the advantages and disadvantages or limitations. For the advantages, accuracy provides precision in calculation of moments for continuous beams, leading to safer and more efficient designs. Now when you break down this and you break it down to the simultaneous equation, you are certain that it is no longer a cumbersome calculation or complex calculation to carry out now. It is something that you are very sure that once you apply your simultaneous equation, just basic mathematics, you are good to go. The versatility, applicable to various loadings and support conditions, including support settlements. This is another aspect of it. It is versatile. No matter the loading condition, no matter the supports, you can use three-moment equation. Simplicity, it reduces complex indeterminate problems to a system of linear equations that are easier to solve. I said for this accuracy, it is once you break it down to just linear equations, then you are good to go. You are good to go. So the limitation now is complexity. Now depending on the number of supports, when you now have complex number of supports, then there's a problem. because the equations, you have so many equations. Not that you must get the answer you're looking for, but it will be very, very long, like start solving very long because of the number of spans. So assumptions. Now the limitation is assumes, it makes some assumptions. It assumes linear elastic behavior of materials, small deformations, constant moment of inertia, and modulus of elasticity, which may not be accurate for all scenarios. We cannot predict that a material is perfectly elastic, or is linear perfectly elastic, or the deformation that is formed based on the applied load is very small. But then it gives you an approximate value that is accurate. So let's move to the next part of this now. So for the next part of this, we are looking at the illustration. Looking at this, this is now, we call it a 3-span continuous beam. You have span L1, L2, L3, subjected to a point load between span A and B, that is L1. Then uniform distributed load between span B and C, L2. Then a point load that is not centralized, P2, between span C and D, that is L3, that is the span. So A to one side, B to one side at the distance. So this is a 3-moment expression that was developed by Clapeyron. So it's saying this, what this means is that the moment multiplied by the length of that span, then modulus of elasticity, modulus of inertia of that span. So you're just taking each span separately. This, at this joint here, you only have, at this support A, you only have this portion. So the LAB, that is LAB, this is it here. So the next one too, you take the same thing. This B is supported on two sides. This portion AB and portion BC. That's the reason why you have AB plus BC. MB is constant for both sides. On support C, since we are already breaking down, I told you we are going to consider 3 supports, 2 spans, in order to apply successfully our 3-moment equation. So this support C is the last one. That is why you have it, and it's only supported by BC. Now you have MC LBC over EIBC. Then you have this expression. So where each of this item or each of this is represented. MA is moment at point E, MB is moment at point B, LA length of span between supports A and B, like I told you, LBC same thing between support B and C, E modulus of elasticity, I moment of inertia between span AB of this portion, X centroid of free bending moment between support AB. Same thing for BC, the same thing. Area of free bending moment for both AB and BC. So this is how the 3-moment Clapeyron expresses 3-moment equation, and he's using it to solve the equation so that it will be easier to understand. Now, looking at this same expression, we want to break down some things. Instead of now calculating centroid and calculating area and all these things based on the bending moment diagram, it has been simplified. And that simplification is what we are actually going to consider here. It has been simplified. So for beam with uniform distributed load, where you have 6AX, so that it depends on the span. So for uniform distributed load is now taken as WL cubed over 4. For beam with point load at the midspan is represented as, expressed as 3PL square over 8. For beam with point load anywhere along the beam, this is it, this is the expression here. Now we should note, for this anywhere along the beam, if we are considering span B, C, D, the dimension closer to the external is what we are going to impute here, and that is the reason why I have this here. Understand this, the values of A or B is dependent on the dimension closer to the end support. If I'm considering span BCD, where I have the point load that is not centralized, here I have this is the load P, B is the distance to the end support, then L square minus B square over L. Assuming it was this portion was around here, I'm considering BCD. A will not be water because A is closer to the end support. So I hope you understand this. Just take time to understand this thing that I just explained now. So now let's move over to the main thing. Now the steps in using the three moments equation. We have different steps, so you need to take it step by step so that we are not going to get confused along the line. And then these steps will guide you in such a way that you will not even know when you finish solving everything. And we just have 6 of them. Now the first one is divide the continuous beam between supports and identify the type and magnitude of loads acting on each span. What this statement means is, here this is what I have here. I'm dividing, I have 4 spans, 4 supports, A, B, C, D, 4 supports, span AB, span BC, span CD, that is 3 span. So I'm going to break it into 2 span, 3 supports. Look at it, A, B, C. I've broken it down here. B, C, D. This is another 2 span, 3 supports. You understand them? And then the loads, you look at them, you consider them. Okay, let's look at the second one. Say apply 3 moment equation for each set of 3 consecutive supports to relate the moments at these supports, just as we talked about here. To take A, B, C. A, B, C. Are you seeing it? So we take it, 3 supports, consecutive 3 supports, we take them together. So the next one is, so after taking, depend on the number of spans you have, depend on the number of spans, so that will now help you to determine whether you are going to use simultaneous equation or you are going to use matrix method to solve, depend on the continuous beam, number of spans in your continuous beam. So solve the system of linear equation simultaneously to find the bending moment at the supports. Yes, you understand what simultaneous equation is. Now you determine the reactions using equilibrium equations. Also determine the shear force and the maximum bending moments. The last one is draw the shear force diagrams and shear force and bending moment diagrams. And this is what we mean by bending moment diagrams and shear force diagrams. So one of them is representing the maximum bending moment due to the applied load, and then the other one is showing the bending moment at supports. We have bending moment, combination of bending moment at span and bending moment at supports. So gradually we understand these steps and know how to go about it. So if you are ready, let's get started in our calculation. So this example, we are considering this span. Draw the bending moment and shear force diagram for the 3 span continuous beam shown below. Assume EI is equal to constant. E is the modulus of elasticity, I is the modulus of inertia. So this is it, what was given to us, A, B, C, D. This is 3 span, 4 supports. And from our steps, the first thing is to do is to divide the continuous beam between supports, taking 3 supports at the same time. So we have A, B, C, and this is what I have represented here, A, B, C. I hope you are following. Then the other one is say 3 consecutive. So after A, B, C, the next one is B, C, D. If I have another span, it will be C, D, E. If I have the next one, D, E, F, just like that. That is how we are just going to keep doing this. We are going to generate simultaneous equations. Okay, so looking at this now, divide the continuous beam into supports. So I have divided with A, B, C, B, C, D. And then the loading conditions, uniform distributed load for span AB is here. I have a combination of uniform distributed load on span BC and a point load that is not centralized on the same span BC. So The same thing here, BCD. What we have here is what I have represented here. Uniform combination of uniform distributed load and point load on one point here, and then the uniform distributed load on between span CD. Okay, so this is let me just recall. For the 3-span continuous beam with end supports simply supported at points A and D, the moment MA equals MD equals 0. I don't know if you understand this statement. So for the 3-span continuous beam with end support simply supported, that you have the ends are simply supported at point. So for the end at point A and D are simply supported and they are the ends. So they are telling that the moment at those portions is equal to 0. MA equals to MD equals to 0. Did you get that condition? Then this other one, then the moments about supports B and C are unknown. These ones are at the end. Automatically they are 0. MA and MD are 0. So the ones we are going to look at the moments at this support, MB and MC. I hope we understood this first part. We divide the continuous beam between supports. Now let's look at this next one. The next stage says we should apply 3-moment equation for each set of the consecutive supports. So for span ABC, continuous span ABC, this is the stuff. So this is the 3-moment expression for it. MALAB over AIB and all this MC, so it's ending at MC. So now expressing based on the loading conditions. I told you that we don't need to start calculating the area based on the maximum bending moment, the central based on the maximum bending moment has been simplified to reflect with the load there. So expressing based on the loading conditions, this expression is still the same as what we have here. So for this uniform distributed load, it is WL cubed over 4, as I showed you initially. We have a combination of 2 here. Then this is for the uniform distributed load, it is still WL cubed over 4. Then for the point load that is not centralized, I'm having PA L square minus E square over L. Now I'm just calling it A because I don't want to interchange certain things. I just want to call it PA. So A represents the dimension closer to the end support. The dimension closer to the end support. That's what A represents. Assuming it was B, the same thing. B will represent the dimension closer to the end support. Okay, so ignore the negative sign since it indicates that the moments are hugging. This negative sign, you ignore it. Also, EI equals constant according to the question, that is equals to 1. MA equals to MD equals to 0. Simply supported ends, as we said, we have the 2 ends at A and D are simply supported, so we call it 0. So substituting all these values now that we now get now, our distance, the length of AB is 6 meters. So 6 multiplied by moment at A equals to this dimension here. So we have this now. This one equals to 1. MA equals to 0. So 6 times 0 plus 2 MB, 6 plus 5. This is exactly as 1 as stated in the question. Then for our uniform distributed load span AB, the magnitude of the load is 40 kilonewton per meter. That's 40 multiplied by the span 6. You manipulate it. For this other span, for the uniform distributed load is 20 and span is 5. Are you seeing it? Then for this our point load, the dimension that is closer to the end support, that is 3. That's why you have 3 here. You do get. So when you manipulate it, you get it your first simultaneous equation. That's this here. Let's move to the next. So we consider the next span. Span BC. So this is what we have here. This is the span. We do the same thing we did before. Expressing is MB, MC is one at the center, so we have it here. MD, this is it here. area centered and the rest. So expressing it based on the loading condition. Here we have point load and uniform distributed load. So uniform distributed load is WAQ over 4. The point load, look at what I said here now. My A now is now 2 because it is closer to this end support. This is B. This is the dimension is closer to, so it is now 2 here. Represented as 2 here. You understand me? Then at this portion here, we have it as this WAQ over 4. Uniform distributed load. So considering this condition again and substituting, we have our value 20 for uniform distributed load for this first span multiplied by 5. You have it. So 80 multiplied by 2. Our A here is represented as 2 because this is dimension closer to the end support. Can you see it? So for this other span CD, 40 multiplied by 6, that is 6 cube, is the dimension for this span. So manipulating it and adding, you have this as second equation. So the next thing we are going to do now is to move to the next step, which says we should solve simultaneously. So we got the first equation from considering the two spans ABC. The next one we got using considering that one of BCD. So this is what we got here. So solving simultaneous equation, we know how to get simultaneous values, right? So this value now is now this multiplied by this 110, 5 times 5, 25, 5 times this value will give you this. Same thing here, this multiplied by this, coefficient of this multiplied by this will give you this. So when you subtract these values, you have this minus this, you have this, and this. MC equals to this value. So this is our moment at support C. This is what it is. So now we are substituting this value in equation 1. This value for MC in equation 1. When you substitute it, you get your MB as this. So you are now have your moment at support B and C as these values you have here. So MA equal to 0 kilonewton meter M support. MB has been calculated here 132.64. MC has been calculated to 126.99. MD 0 kilonewton meter. I hope we understood this part of it. Okay, so let's move to the next step. Now the next step is to determine the reactions using the equation of equilibrium. And using the equation of equilibrium, we need to have one span, and then the number of redundancy will not be more than 3. So now summation of vertical forces equals 0, as upward force equals to downward force. Upward force is reaction at A and reaction at B. So at this portion, I'm calling this B as B1. Maybe we have another support between B is supported towards A and also towards C. So RA plus RB1 equals to 40, converting this into point load, 40 times 6. This is why we have this. So this is another equation. So taking moment, summation of moment around B, point B equals 0. So taking moment about point B. Clockwise moment is positive, anti-clockwise is negative, what I consider here. So I have RA going towards B in a clockwise manner is multiplied by 6. That is why you have this here. Then this other portion here, 40 coming towards B is anti-clockwise. That you have a negative sign here. 40 multiplied by 6 times 6 over 2. This, our moment at B is clockwise. So plus 132.64 equals to 0. So manipulating this, you have the RA as 97.89 kilonewton. Coming over, so we are going to substitute this value for RA in this equation here. So when we substitute it, we have the RB1 as the reaction at B at 142.11 kilonewton. So I always like to check anytime I perform this equation stuff so that I know that I am doing the right thing. So the check is, I took moment around point A, so I'm taking moment at point B. Now I want to take moment around point A to be sure that this value I got here is actually correct. And so this is it here. Remember, clockwise movement is positive, anti-clockwise is negative. I hope you understand. Okay, so now from RB1 times 6 is coming in anti-clockwise manner. That is why minus RB1 times 6. Did you get that? Then this uniform distributed load is coming in a clockwise manner towards A. So 40 times 6 times 6 over 2 plus our moment around support B is positive, is the clockwise direction. So manipulating it, we have this as 142.11, which is corresponding to what our value we got here. So this check is correct. Did you understand? Hope you understand. So this was span AB. So we are going to look at span BC and do the same thing for span BC. So for span BC, this is the span and this is the forces acting on that span. We have the uniform distributed load and point load. Then you have the moment at point B and also moment at point C. So summation of vertical force equal to the upward force equal to downward force. RB2, may be called B1 as in span as a span AB. So you are calling this on B2 now. Then this is C1. Hope you understand. So RB2 plus RC1, this upward moment equals downward moment. So 80 is 20 times 5. So this is what we got here. I hope you understand. I hope you understand this. So take moment about point C. Summation of moment at point C equals 0. So this is at this point here. So we are taking from B down to C. So RB going in clockwise direction is positive. So RB1 times 5. RB2 times 5, sorry. Did you see how it came about? RB2 times 5. Then this uniform distributed is coming downwards and anti-clockwise direction. So 20 times 5 times 5 over 2. Then we have this other portion here. 80 multiplied by 3 because it's coming anti-clockwise. Force times distance. It's force multiplied by distance to get to this portion here. Then at point C, we have these are moments, clockwise moment that is positive. At point B, we have anti-clockwise moment that is negative. Since we've already considered this moment between span A and B as positive, as clockwise, so when this is going the other direction, we convert it as negative. So manipulating this, you have RB2 equals to 99.13 kilonewton. Substituting this value for RB2 in equation 2, you have your RC1 as 80.87 kilonewton. I hope you understand. Just take your time and understand this principle. It's just a repetition of what you have done before. I'm just taking my time to explain this so that what you did not catch the first time, you're going to catch it now and understand it very well. So check. Since we took moment about point C, so we're going to take moment about point B as a check. Anti-clockwise moment is negative, clockwise moment is positive. So I will see multiplied by 5 to this portion here, force and distance. That's why I have this. Plus, this man is coming down with this uniform distributed load, coming in a clockwise direction towards point B, 20 times 5 times 5 over 2. So, for our point load, force 80 multiplied by distance to B is 2. Then, our moment did not change. Clockwise moment is positive. This is it. Anti-clockwise moment 132.64 is negative. Is this? So when you manipulate it, you have a RC1 as 80.87, which is coinciding with what we calculated initially here, when we substituted the value for RB2 in equation 2. Did we get that too? Okay, let's move to the next span. The next and the final span is for span CD. Now this is what we have on span CD. We have our support moment 126.99 in anti-clockwise direction. At D it is 0 because it is the end, simply supported at the end, support at the end. Summation of vertical forces is equal to 0, upward force equal to downward force. this and this upward ROC to ROD equals to this our load 40 times 6 point load. So the next thing we are going to look at is summation of moment around D equals 0. At this point equals 0. So this portion clockwise movement to D, first ROC times 6, we have it here, minus this is going to come downwards anti-clockwise. So 40 times 6 is point load, then we are acting at the center, 6/2 minus anti-clockwise support moment. Manipulating it, we have ROC2 equals 141.17 kN. Same thing as we did initially for others. This value, substituting it for ROC2 in this equation 3. When you substitute it, you have your ROD as 98.83 kN. To confirm your check again, to perform your check again, we still do the same thing. So summation of moment about point C equals 0. So ROD multiplied by 6 anti-clockwise, I have minus. Uniform distributed load converting the point load times 6, acting at half of this distance. This is what you have here. The support moment doesn't change, so far the convention is not changing. Anti-clockwise moment minus. So substituting it, we have this value. So it has confirmed that what we have calculated here is correct. So having done that, let's get everything together. Let me get everything together and then express it. So this is it, RA from our calculation 97.89, RB. So now we have this support, RB1 is towards this side, RB2 is towards this side. So both of them are together to be the reaction at this point here, portion here. So the reaction at B, RB1 plus RB2. RC the same thing. RC1 is towards B, RC2 is towards D. You add both of them together, it gives you this 222.04 kN. Then RD, our reaction, we have it as this. So we express it in a free body diagram like this. So we are able to understand this is what we have done. So the next step is to find the maximum bending moment and shear force values for this load. Now, so maximum bending moment for this span, we calculated support moments already. Now I want to calculate span moments, and this span moment is this. For uniform distributed load, the maximum bending moment for uniform distributed load is expressed as W squared by 8. So W is the load there. Are you seeing it? So 40 multiplied by 6 squared divided by 8. I have it as 180 kN. For uniform distributed load and point load and span, BC, M max. So for the uniform distributed load, maximum moment is WL squared by 8. Then for point load, not at the center, PL over 4. Did you get that? For point load, not at the center, PL over 4. Okay. So when you manipulate it, you add them together. Since they are both acting in unison to the effect, we now produce 162.5 kN. Then for span CD, you have 40 and 6. So this is the expression W squared by 8. You have this 180 kN. Are we good? So we move to the next. So now, this next one now we need to be very, very careful. I decided to do this on a separate page so that we are going to be able to understand what or how to calculate the shear forces both at the support and at the span. Now is the kind of a combination something. For the moment we did for span moment and support moment. Now for the shear force we are also doing the same thing. For the support, those are the reactions. Then the shear force at the span, this is how we calculate it. So let's start. At point A, the shear force is equal to the reaction at A. And that reaction at A from what we calculated is 97.89. You get that? That is for the support shear force, is maintenance, the reaction, and those other support. So now, at span AB, understand this. At span AB, this is our value here. Will that be upward minus downward? So converting this into downward, that is 40. Since there is no other dimension up till point B, so we have it as WL, that is at x equal to 6, RA minus, this is upward force minus downward force to get the shear force between this span. So RA minus WL. So RA we calculated it here. W 40, L 6, 40 times 6. When you manipulate it, you have minus 142.11 kilonewton. Keep that one. Now the shear force at B will now be this initial shear force you got here plus the reaction. You know here we said VA is the shear force equal to the reaction at A. Then at this point B, we already have, after calculating this for this span, you have the value here. Now the shear force will now be this reaction plus the value for the span shear force. That is why we have VAB, this value here, VAB plus the reaction at B. So when you add it all together, I have this value 99.13 kilonewton. I don't know if you understand. So we've gotten this at this point B. So we are moving forward to point C. Between span BC, we have break in dimension 2 meters first and then 3 meters before you get to C. So let's take it step by step. So for the shear force at VBC1, the reason why I said BC1 is this is the span BC. So from here to this portion here to this 2, that is BC1. Then from there, based on this point load BC2, come here BC3. I don't know if you hope you understand, but let's just take it step by step so you understand. Now VB minus WL at x equals to 2. VB, what we got here, minus, the reason why it is minus because it's downward force. Downward force, now you have uniform distributed load at this portion here. This small portion here. You have it as this portion here. So this point load is what is dividing it. So this uniform distributed load is the same along all the span. Whether the dimensions are equal or not, is the same. That's why you have the magnitude of 20 kilonewton. That have 20 multiplied by the distance 2 at x equal to 2. When you manipulate it, you have this. Now VBC2 will now be this value that you got now minus this point load is already acting minus this point load at this same point 2. From B to this point 2, we also have another one acting at this point 2, so we need to deal with that, and it's downward. So this minus P, that is the point load, we have this value here. Now we are moving VBC3. So from point 2 now, we are going all down to C at the distance of 3. So this value minus WL at s equals to 3, because this is the remaining portion that is remaining. S equals to 3. So this is our value VBC2 minus this to 20 multiplied by 3. When you manipulate it, you have this value here. For VC, when you get to VC now, we have our reaction. So this value plus your reaction, why it is plus because it's the upward force. Manipulate, you get this. As span CD is just straightforward. So maybe this VC minus WL s equal to 2, s equal to 6. When you manipulate it, you have this value here. Then at VD, now the VCD, this value plus the reaction at D. So the reaction at D, when you add it up together, you have 0. I hope I will not confuse you, but I believe this explanation is self-explanatory. That's the reason why I made this explicit, like so that you understand step by step how we came about these values here. Okay, having understood this, we move over to the next step, which is to draw the bend moment and shear force diagram. So this is the free body diagram that was given to us, the loading conditions, uniform repeated load, uniformly and point load, uniform repeated load. So that moment diagram, I told you we calculated the support moment. We calculated the support moment and we also calculated these are the support moments at point B, at point C. Then we also calculated the maximum bending moment based on the span. The maximum bending moment, these values. So maximum, so that is what we use in calculating this. So for the span, this is 180 kilonewton meter for this span AB. For this span BC, 162.5 kilonewton meter. As you see, this effect, it is coming as a curve, but when we got the effect of this point load and this moment load, it makes it to have this parabolic shape from this point where the point load is acting. So for this other portion, so this is 180 kilonewton meter. That is for the span maximum bending moment. Span maximum bending moment. Then for the supports, as we calculated, A and D are the end, so they are 0. Then from what we calculated, for the support moment, we have MB at 132.64, MC at 126.99. So that's the same thing we are going to replicate here. 136.64, 126.99. And we are not just writing these values, just like 0 to 180. 180 is the highest point here. 162 is the next. So 132 is normally supposed to be below 162. So that's the reason why I have the 132 is here, 126.99 is here. So what we do is to join the point to A to support B, support C, support D. Then so the bending moment now will now be captured between the positive part is where you have the span moment that is above the support moment, the line. This is it here. Therefore, the part where you don't have just the span moment is you don't have any support span, so you have this negative. Here you have it as positive. You have it as negative. You have it as positive. So for the shear force, what we calculated here, we are going to replicate it here. So at point A, 97.89. This is it here. When you come down to this portion, you have minus 142.11. Are you seeing it? Come to the next one, up here, 99.13. The reason why it's going up is positive, up is positive, down is negative for this. Up is positive, down is negative. So 99.13 is positive. For this portion, 59.13 from BC. As it's still under positive, 59.13. Then coming down 20.87 down to this portion, up here, down, and 0. So I hope you understood this. You just take time. If you don't understand this, go back to this video, you watch it over and over again to understand how these values were gotten. So upward, as I told you, positive, downwards is negative, positive, negative, positive, negative. So in conclusion, three-moment equation is a powerful tool in structural engineering, enabling the analysis of continuous beams under various loading conditions. By relating the moments at three consecutive supports, it provides a systematic approach to solving indeterminate beam problems. Have you seen how easy it was? Unlike the three moments, like the moment distribution method, whereby you may carry over and all those kind of operations, this is very straightforward. Just dividing into three supports and you are good to go. So despite its complexity, it remains a cornerstone of structural analysis, offering accuracy and reliability when its assumptions are met. So I hope I have been able to explain this three-moment equation very well for you to understand the principle and see that it is actually easy, and based on what it is claiming that they are offering accuracy, it is actually accurate. It's simple. You just have to take your time and understand each of the process. Thank you very much. See you in my next video.